Okay, my name is Jinho Ahn at Seoul National University. My talk is about ice core record from Antarctica and Greenland, focusing on change in atmospheric CO2 during abrupt climate change. Arana already introduced about the abrupt climate change, so it's very good. So first I'm gonna explain some details about some background of carbon cycle and abrupt climate change. And then I'm going to compare two different types of abrupt climate change. One is during last glacial period, and the other one is during interglacial period. And actually it's two different timescales, but it will be interesting if we compare the response of atmospheric CO2 during two different climate boundary conditions. This is a well-known curve. It's called killing curve. So city killing measured atmospheric CO2 since late 1950s. As you see, you can see the seasonal variability, also interannual increase of CO2 now is almost 400 ppm, parts per million. So, but this record is very limited, and we know the CO2 increase by human activity like fossil fuel combustion and land use change and cement production, but we don't know how CO2 behaves because this record is too short, and the lifetime of CO2 in the atmosphere is hundreds of years or more. So, and this is to understand the atmospheric CO2, we have to know about size of carbon in ocean and land, and also carbon exchange between atmosphere and ocean and land. The red numbers indicate the relative size of carbon. As you see, the size of carbon in the atmosphere is relatively small compared to the carbon in the ocean and inland. This is a pre-industrial case. That's the before human activity, disruption of carbon cycle by human activity. But now on the top of the natural cycle that's indicated by black arrows here, we see red lines. It means anthropogenic perturbation of carbon flux between ocean and atmosphere and land. So as you see, atmospheric CO2 concentration is determined by this carbon exchange. Therefore, some physical and biological condition in the ocean and land is very important. And also the condition of this land and ocean can be affected by climate itself. So we have to consider feedbacks. So, for example, this is just ocean case. CO2 exchange can be controlled physically by temperature, simply. CO2 dissolves more in cold water than warm water, and also biological activity control affect the CO2 exchange by photosynthesis and calcareous shell formation. And so when you consider the feedbacks, the future CO2 level, predicted CO2 level will change. For example, only one emission scenarios. For example, these scenarios, different models give different results about the CO2 level because each model has different feedback models. So there's huge difference of results, and that corresponds 20 to 200 ppm. But the common thing is they all says it's positive. It means additional CO2 increase by feedbacks. That increase additional temperature around 0.1 to 1.5 degrees C, but it's broad range. So it means our understanding of the carbon cycle is very limited. So better understand this carbon cycle and climate change, we need some more information. So now I want to show the ice core record. That if you see ice core, there are lots of bubbles. That is the ancient air preserved in glaciers. So we use this kind of stuff. This is one of the experiment facility in our lab. So we use this kind of needles and crush the ice and break the bubbles and extract air and analyze CO2 concentration. So this is the ice core record for the last 1,000 years. From 1000 AD, you see the CO2 level was around 280 ppm with just a few ppm variations. And then since industrial revolution, you see James Watt here. So you can see abrupt rise CO2. And the red line indicates the instrumental measurements by city killing. So very good agreement around this time interval. And you see the background level of CO2 should be, must be around 280 ppm. Now, Arana already shows this kind of graph, but this is a paleoclimate record. We usually plot this on an age scale. So time goes from the right to left. So this scale of 1,000 years, so it's 800,000 years ago, 600,000 years ago, and now. You see Antarctic temperature change, glacial interglacial cycle, and CO2 and methane. And so now it's around 400 ppm, very high. It's not happened before for the last 800,000 years. This is what we know already, but we don't know much about the exact relationship between CO2 and climate, and how CO2 is affected by climate, how CO2 affected climate. And also, what controls atmospheric CO2? Is there any principle that controls atmospheric CO2? So to do that kind of study, we need high-resolution record, especially during abrupt climate change events. So I'm going to focus on two different time intervals. One is during last glacial period. The other one is the current interglacial period. So this is ice core record from Greenland and Antarctica. These two ice core records are synchronized with methane correlation. So this methane from Greenland ice core, this methane from Board ice core, and we can synchronize, match one-to-one, and synchronize ages. Then we can directly compare the timing of the relative timing of the temperature change. So if you see Greenland record, you see abrupt warming. So this is also age scale. So time goes from the right to left. So if you see here, rapid warming, slow cooling, and left cooling. So this rapid warming is just around 10 degrees Celsius degree, and it just happened 5 or 20 years or just a few decades. So this relatively warm period is called interstadial. The cold period is called stadial. So cold stadial, interstadial repeated many times, and the change of these two different climate conditions is so fast. And this kind of event is called Dansgaard-Oeschger event after the scientist's name. And we found more than 20 times during last glacial period. And however, Antarctic temperature is not like Greenland. As you see here, during cold period here, you see increase of Antarctic temperature. After warming in Greenland, you see cooling in Antarctica. So it's opposite phase. So how can you explain this kind of abrupt feature of climate and also climate link between Greenland and Antarctica? So there are hypotheses, but one of the leading hypotheses associated with ocean. So this red one is surface ocean, surface flow, and blue one is deep ocean flow. Actually, there is a deep water formation in the North Atlantic because North Atlantic is relatively saltier than other oceans. And at cold temperature, the density increases and the water sinks and it forms deep water. This kind of water sinking makes this kind of flow pattern. So we call it meridional overturning circulation. Actually, this is not simply ocean circulation. It also transports heat, thermal energy. So by the ocean, the net effect of heat transportation is from the southern hemisphere to the northern hemisphere. So what happens if there is stop of this ocean flow? We might expect cooling around this area and warming in this area. That's the simple idea. So this is a simple model. So this is called bipolar seesaw. So it's a kind of thermal energy at time t, something like this. And North Atlantic, South Atlantic, if there's the ocean flow, we might expect heat transportation from the southern hemisphere to the northern hemisphere. If there is stop, the temperature would increase in the southern hemisphere. And if you simply add some heat reservoir in the southern hemisphere, we can do some simple models. For example, this is Greenland ice core record. You see abrupt features here. And if you input this data to this model, the result is here. And actually, the Antarctic ice core record is here. It's very similar. So physically, it's possible this kind of climate link can be explained by ocean heat exchange. But this is not my interest so far. So my interest is carbon dioxide and carbon cycle. So my question is, how is atmospheric CO2 linked to abrupt climate change? So first, I want to compare CO2 and climate, the relative timing. And second, CO2 with oceans, the meridional overturning circulation. This is my study results. So top one is Greenland climate. You see abrupt warming features here. And this is Antarctic temperature. And this is CO2 record from the same ice core of this temperature proxy record. And as you see, in general, CO2 is more like Antarctic climate. It's not like a Greenland climate. And it means CO2 increases during the stadials, Greenland stadials, and CO2 decrease during cooling event in Greenland. But this data is only during long and strong high-need stadials. The details of this CO2 change during these stadials, I'm going to talk it a little bit later. So when I analyze this data, so CO2 increase relative to abrupt warming in Greenland, you see CO2 started to increase several thousand years before the abrupt warming, and then CO2 stays high and then decreases later. Sometimes we see abrupt CO2 increase, jump of CO2 at the same time of abrupt warming in Greenland. This is from Bird ice core, one of the Antarctic ice core, and two different other Antarctic ice core confirmed our data. So what about the ocean circulation? Ocean circulation transport not only heat but also chemicals that could affect biology. So, and heat exchange of physical property of the ocean. So this is CO2 record from 80,000 years ago to 20,000 years ago. And this is slope of this one, just derivative of CO2 record. And when you compare it with ocean circulation proxies, we see rapid rise of CO2 happened at the same time of weakening of North Atlantic deep water formation. That time, we also see kind of less stratification in the Southern Ocean. So less stratification means upwelling of deep water to the surface. So the CO2 rich deep water reaches to the surface, and that provides CO2 to the atmosphere by gas exchange. People interpretation. This is model results if we do coupled climate carbon cycle models. So this is if we input some fresh water to the North Atlantic. So fresh water has low salinity, therefore low density. Low density would prevent a deep water formation. So it means stop of this heat transportation. That would increase the deep water formation or Atlantic overturning circulation in the North Atlantic, and cooling in Greenland temperature, and increase of Antarctic temperature, also CO2 increase. According to this model, we don't know exact mechanisms, but what we found is less acidification in the Southern Ocean. It means more upwelling of deep water to the surface and providing more CO2-rich water to the surface, therefore CO2 increase in the atmosphere. Now I'm going to talk about the more high resolution record. So this is Greenland ice core records. Now you are familiar with this kind of abrupt features here, and these three are from Antarctic ice core. So I already mentioned about the CO2 and Antarctic warming around these long and strong stadials, Greenlandic stadials. But now my question is, what about these short stadials? So if we compare the duration of stadials and warming in Antarctica during these Greenland stadials, we see positive correlation. So we can simply explain this one because there is stop of the heat transportation, Antarctic temperature would increase. That should be positively correlated with the duration of the stop, duration of stadials in the Greenland. So what about CO2 during these short stadials? Because CO2 and Antarctic temperature is very positively correlated, so many people think the Southern Ocean played very important role. So to answer that question, we need very high resolution records. So I used Siple Dome ice core from West Antarctica that has a relatively warm temperature. Being annual temperature is negative 25 Celsius degree, and snow accumulation rate is 12 centimeter water equivalent per year. Using this ice core, I obtained a very high resolution CO2 record from 44K to 22K. So this is Greenland ice core record, and this is CO2 from Antarctica Siple Dome record, and this is Antarctic temperature from Siple Dome and EDML ice core. So two different ice cores. So the pink line here indicates strong and long stadials, and blue line indicates relatively short and weak stadials in Greenland. Now you see CO2 increase during long and strong high-need stadials in Greenland, but no significant increase during these short stadials. So there is two different types of CO2 response. So if we plot just CO2 relative to the duration of Greenlandic stadials, the CO2 revolution is like two patterns. One is just increase. The other one is no increase. These two types. What about temperature? So temperature is most of Antarctic temperature increase during all the stadials except this one. This is very exceptional just in one ice core, but different ice core shows warming in Antarctica also. So if we reject these results, now we can plot CO2 versus Antarctic temperature. So one mode is positive correlation that happened during long and strong stadials in Greenland. The other one is no CO2 increase during short stadials. So one might say, what about delay of CO2 response to change of ocean circulation and climate? If then we would expect no increase of CO2 from the beginning of this side. So we might expect no change of CO2 and then increase this way. But the ice core record does not show that way. It shows the increase of CO2 from the beginning of this abrupt event. So it's not likely simply time lag problem. Instead, we propose that there's some critical oceanic that control the mode of CO2 change. And that difference in strength of the perturbation make different response of Southern Ocean. So a valley in the Southern Ocean during short stages might have not deep enough to draw CO2 reach the water to the surface. That's our current interpretation. And actually, this paper supports our idea that if you would plot the duration of Greenland stages and Antarctic temperature increase, there's two types of sensitivity. This side is more sensitive than this one. So it means probably this kind of warming event and the long stages in Greenland probably strong perturbation in the climate. So this is summary about first part of my talk. That is, CO2 is more like Antarctic climate. And we observe CO2 increase during long Greenland exterior period. And that happened during weakening of North Atlantic deep water formation and less stratification in the Southern Ocean. However, CO2 neither increases nor positively correlates with Antarctic warming during short or weak Greenland stadials. So it is likely that there is a critical threshold in strength of oceanic perturbation to change atmospheric CO2. Perhaps a dwelling in the Southern Ocean during short stadials was not deep enough to draw CO2 rich deep water to the surface. So second part is about the abrupt warming, abrupt climate change during interglacial climate condition that happened around 80 to 100 years ago. This is Greenland ice core record. So this is depth scale, and this is age scale. So it means 10,000 years ago, 6,000 years ago. So you see the early bit warming after deglaciation, and then abrupt cooling around 800 to 2,000 years ago. So different color indicates different ice core record. So many records shows abrupt cooling event for 160 years. So it's two-step, one drop, second drop, one step increase, second step increase. So that happened around for 160 years. So it would be very interesting carbon cycle experiment. So what would happen in the atmospheric CO2? How is atmospheric CO2 responded to this abrupt climate change? Also, many paleo proxy records show cooling event around North Atlantic and dry and windy conditions in Asia and Africa during this event. And also, some model study shows more than 5 degrees C cooling in the Nordic Sea and cooling over the Europe, and probably slight warming in Antarctica. So what happened 8,200 years ago? One of the leading hypotheses associated with ocean circulation again. So this ice sheet is shrinking from 11,000 years ago to 7,000 years ago. If you see around 9,000 years ago, there is one block of ice sheet and two lakes, pro-glacial lakes, Lake Agassiz and Obisway. And then if you see the next one, around 8,000 years ago, there's opening of passage here. So we expect lots of fresh water here in the lake provide lots of fresh water to the North Atlantic. So fresh water has low salinity, therefore that will decrease of density in this North Atlantic and stop the deep water formation. It means stop of this current. Therefore, cooling in Greenland and North Atlantic area. So we need high resolution CO2 record. So I use Siple Dome ice core again. This Greenland ice core record, this is Siple Dome CO2 record. And to define the exact timing of Greenland cooling, I used methane correlation. So this methane record from Greenland ice core, this red one from the same ice core here, Siple Dome. So methane is trace gas that has 10 years ago. And so the methane decrease, change of methane in the northern hemisphere should have the methane decrease in the southern hemisphere. So which exactly matches the timing of the abrupt cooling event in Greenland, and I colored with red, with yellow here. If you see CO2 record, there's very little increase of CO2, but that change is just order of centennial CO2 variability. It's not significant. So it's interesting. The abrupt cooling event does not affect atmospheric CO2 level. So this is summary. Abrupt cooling event at 8,200 years ago is most prominent abrupt cooling event at interglacial boundary conditions. And we observed very little increase of CO2. This magnitude is comparable with just centennial variability. And our data imply a limited sensitivity of CO2 to climate change in Northern Hemisphere during abrupt cooling event 8,200 years ago. Thank you for your attention.